Right now, about 2,900 kilometers beneath your feet, there is something down there that isn't supposed to exist. Not lava, not rock, not in the way you picture rock. Something else, something the size of a continent, sitting on top of the molten core of this planet, and it is chemically foreign to everything around it. Nobody has seen it, nobody ever will. No drill, no camera, no probe built by human hands will ever reach it, and yet we know it's there, sitting in the dark, the way you know there's a shape in a dark room by the sound your voice makes when it bounces back. Here's the part I need you to sit with for a second. There are two of these things. One under Africa, one under the Pacific. And a growing number of scientists now think they are not pieces of Earth at all. They think it's the wreckage of another planet, a world that died so that the moon could exist. And instead of vanishing, most of it may still be down there. Not melted, not mixed in. Still separate, 4.5 billion years later, like oil that never quite blended into water. Every full moon you have ever looked at, every single one, is a leftover of a collision so violent, it should be unimaginable. And what I'm about to walk you through is the possibility that the other half of that collision, the actual body of the thing that hit us, never left. It's still here. It's underneath you right now, while you're watching this. I want to be honest with you before we go further, because that's the whole point of doing this properly. What I'm describing is not settled. It's one of the most contested ideas in modern planetary science, argued about in journals as recently as the last couple of years. There are other, more established explanations for what's down there, and I'm going to give them a fair hearing too. But the story of how we found these things, what they might be, and what it means that you have spent your entire life standing on top of them, that part is real. And it is stranger than almost anything else I've come across making this channel. So let's start at the beginning, not 4.5 billion years ago. Let's start in a lab in 1984 with a man reading the wrong signal and finding something nobody expected to find. His name was Adam Dziewonski, and he wasn't looking for a dead planet. He was looking at earthquakes. Here's the thing about an earthquake that most people never think about. When the ground shakes in one part of the world, that shaking doesn't stay local. It travels. It moves through the entire body of the earth, the way a struck bell rings through the whole bell, not just the spot where the hammer hit it. And if you have instruments scattered all over the globe, sensitive enough to catch the arrival of those waves, you can time them. You can ask a simple question: how long did it take that wave to get from the earthquake through the middle of the planet to this specific seismometer on the other side of the world? And if the Earth were uniform all the way through, the same rock, the same density, the same temperature at every depth, the answer would always be the same, adjusted only for distance. Predictable. Boring in the best scientific sense of the word. It wasn't the same. Dziewonski was looking at data from earthquakes recorded at stations all over the planet, and he kept finding these small, stubborn delays. Waves that should have arrived at a certain time were arriving late, if they passed through certain regions deep in the earth, not everywhere, just in specific places. And when he mapped out where those delays were happening, two shapes emerged from the data. Two enormous zones near the very bottom of the mantle, right where it meets the core. One sitting under the African continent, one sitting under the Pacific Ocean, where seismic waves were moving slower than anywhere else at that depth. Slower doesn't mean nothing. In the language of physics, slower means different. It means the wave is passing through material that isn't behaving like the rock around it, something hotter or denser, or simply made of something else. Think about what he actually had in front of him. No image, no photograph, just timing data. Thousands of tiny arrival delays from earthquakes that had already happened, radiating through solid rock a continent away and out the other side. And from nothing but those delays, a shape appeared. Two shapes, continent-sized, sitting in the deepest, darkest part of this planet, in a place no human eye has ever seen and never will. That's the moment this story actually begins. Not with the discovery of what these things are, with the discovery that they're there at all, an anomaly, a shadow, a place where the earth doesn't ring the way it's supposed to. Let that sink in for a second, because I think it's easy to skim past. In 1984, we learned that we could read the inside of our own planet the way a doctor reads the inside of your chest, not by cutting it open, but by listening to how something moves through it. It's the exact same idea behind an ultrasound. Sound waves hit a boundary between two different tissues, and they bounce, or slow, or bend, and a machine turns that behavior into a picture your eye can understand. Dziewonski didn't have a machine that could draw him a picture. He had to build the picture out of pure timing, one earthquake at a time, one station at a time, patiently, for years. But the principle was identical. Something is down there. We can't see it. We can hear its shadow. For the next few decades, scientists kept refining that shadow. Better instruments, more earthquakes, more recording stations, filling in more of the globe. And the two shapes didn't go away. They sharpened. They got names. Scientists started calling them large, low shear velocity provinces, LLSVPs if you want the acronym, though I promise I won't make you sit through that mouthful again. What matters is the low shear velocity part. Shear waves are a specific type of seismic wave, and they are especially sensitive to what kind of material they're moving through. Rigid material speeds them up, something softer or different in composition slows them down, and in these two zones, they were slowing down hard, right at the boundary where the rocky mantle gives way to the molten metal core, some 2,900 kilometers below the surface. The two structures even earned informal nicknames, the kind that stick around a research community for decades without ever becoming official. The one under Africa is sometimes called Tuzo, after a geologist named J. Tuzo Wilson. The one under the Pacific is sometimes called Jason, after a scientist named W. Jason Morgan. I want to flag, honestly, that those aren't official scientific terms. They're nicknames that stuck, the way scientists sometimes name a comet or a fossil after someone they admired. But they're useful, because it's easier to talk about two specific things in the deep Earth if they have names, rather than just coordinates on a seismic map. And these aren't small, each one stretches for thousands of kilometers across the base of the mantle. In places, they rise as much as 1,000 kilometers off the core. That's roughly 620 miles of vertical relief, structures so tall that if you could somehow stand one on end at the surface, it would tower over anything humans have ever built by orders of magnitude. Put together, by some estimates, these two structures make up somewhere around 6 to 9% of the entire volume of Earth's mantle. The numbers move a little depending on which study you read. That's normal for something nobody has ever touched. But even at the conservative end, you are talking about a volume of material large enough to reshape how you think about what's actually inside this planet. Picture it like this. Imagine the Earth is an apple, and somewhere deep inside that apple, not near the skin, right down at the core, there's a bruise. Not a small one. A bruise the size of 2 continents, invisible from the outside, undetectable by looking, only findable by tapping the apple and listening to how the sound changes when it passes through that spot. That's what Dziewonski did, in effect, in 1984. He tapped the planet and heard the bruise. For a while, the leading assumption was the simplest one. Maybe these zones are just hot. Heat slows seismic waves down too, so a patch of unusually warm mantle rock sitting at the base of the planet, maybe near where heat from the core leaks upward, could in principle explain some of what Dziewonski found. It's a tidy explanation. It's also, it turns out, not the whole story. Because later work, more refined seismic surveys, plus careful modeling of how different minerals behave under the crushing pressure and heat found near the core, started to suggest something stranger. At least the lower portions of these two zones don't just look hot, they look denser than the mantle around them. One estimate puts the bottom 2/3 of these structures at around 0.5% denser than the bulk of the mantle. That might not sound like much, but 0.5%, sustained across a mass that size at those pressures, is a serious physical difference, the kind of difference that would let something sit still at the bottom of a slowly churning ocean of rock for enormous stretches of time, instead of stirring in and disappearing like a spoonful of milk in coffee. And the exact density figure is genuinely still argued over. I want to be upfront about that, because it's a pattern you're going to see again and again in this story. Nobody disputes anymore that these two zones exist, What's contested is exactly how dense they are, exactly how sharp their edges are, exactly how old they are, and the part that's about to turn this whole video sideways, exactly what they're made of and where that material came from. Because denser than the surrounding mantle is one thing. It's another thing entirely to ask, denser because of what? And that question is where a very different kind of scientist walks into this story. Not a seismologist listening to the ringing of the planet. A planetary scientist thinking about a much older, much more violent event, one that happened before Earth even looked like the Earth you know. One that, if a particular hypothesis published in 2023 is right, might be the actual source of the two shapes Dziewonski heard in his data 40 years ago. Before I get there, I want you to hold two things in your head at once, because this is the part of the story where we're about to collide, literally. The first thing, somewhere at the base of this planet's mantle, there's a huge volume of material that is chemically different from everything around it and has apparently stayed that way for an enormous span of time without blending in. The second thing, the leading scientific explanation for why the moon exists at all is that a very long time ago, something hit the Earth. Something enormous, something the size of Mars. Most people who have heard of the giant impact hypothesis picture it happening and then picture it being over, a flash of catastrophic violence, some debris flung into orbit, and then a clean split. Earth here, moon there, story finished. What almost nobody pictures is a body count. What almost nobody asks is, where did the rest of it go? Because a Mars-sized object doesn't just glance off a planet and vanish into the void, leaving nothing behind but a ring of orbiting rubble. Most of its material would have been absorbed, slammed directly into early Earth, mixed into an already molten, churning young planet, and then, this is the part that had never quite been asked properly before, settled somewhere. That's the question a scientist named Chen Yuan started chasing. Yuan worked at the seismological laboratory at Caltech, and what makes this story interesting is that he was sitting at the intersection of both halves of what I've just told you. Someone trained to think about the deep seismic structure of Earth, who was also thinking hard about the physics of planetary collisions, two fields that don't usually talk to each other in the same sentence. And the question he and his colleagues, researchers from Caltech, Arizona State, Michigan, and Arizona, started asking was almost embarrassingly simple once you say it out loud. What if the two anomalies Dziewonski found in 1984, the two continent-sized zones sitting at the base of the mantle, are not native Earth material at all? What if they're Theia? Theia is the name planetary scientists use for the object that's believed to have struck early Earth and formed the moon somewhere around 4.5 billion years ago. We don't have a rock sample from Theia. We never will. The object doesn't exist anymore as a separate body. But we do have one piece of physical evidence that survived that collision intact enough to study, the moon itself. And the moon's composition carries a clue. The moon's rocks, brought back by missions that actually touched lunar soil, show an unusually high content of iron oxide, sometimes just called Theia, compared to what you'd expect if the moon were made purely of leftover Earth material. That elevated iron signature has puzzled scientists for a long time. It doesn't perfectly match Earth's own mantle. It's close enough that the giant impact hypothesis still holds up overall, but there's a persistent chemical fingerprint that many researchers have long suspected comes from Theia's own material, mixed into the debris that eventually formed the moon. Here's where Yuan's team made the leap that turned this into a genuinely new hypothesis, rather than just a footnote about the moon's chemistry. If Theia's mantle carried that same elevated iron signature, and there's reason from modeling to think it might have, then iron-rich material is heavier material, denser material. And dense material, dropped into a mostly molten young Earth, doesn't necessarily disperse evenly. It sinks. So Yuan and his colleagues built models, computer simulations of Earth's ancient mantle, freshly disturbed by an impact of that scale, and ran the physics forward. In their modeling, Theia's mantle material comes out intrinsically somewhere between 2 and 3.5% denser than Proto-Earth's own mantle. Not overwhelming, but enough. enough that, in their simulations, chunks of that denser Theia-derived material, initially only tens of kilometers across, scattered through the newly mixed mantle right after the impact, don't stay scattered. Over vast stretches of geologic time, gravity pulls them down through the slowly churning rock above. The way oil poured into water eventually stops swirling and pools at the bottom of the container, staying stubbornly separate instead of blending in. And where does dense material end up, sinking through a convecting mantle over 4.5 billion years? At the bottom. Right at the boundary between mantle and core, the exact depth, the exact location, where Dziewonski heard something strange in 1984. In Yuan's simulations, these sinking blobs of Theia material don't just settle randomly. They accumulate, piling into large continent-scale structures sitting directly atop the core, structures that in the model could plausibly survive essentially intact all the way to today. I want you to actually feel the size of the claim being made here, because it's easy to let it slide past as just another interesting factoid. The hypothesis is not a little bit of another planet got mixed into Earth. The hypothesis is that the largest, most anomalous, solid structures inside this entire planet, 6 to 9% of the volume of the mantle, remember, structures that rise 1,000 kilometers off the core, might not be Earth. They might be the leftover body of the world that had to die so the moon could exist. Sitting there, essentially unmelted into the rest of the planet's chemistry, for 4.5 billion years, directly beneath your feet right now while you're watching this. This is the paper that made the cover of the journal Nature in November 2023, and it's the reason people are still arguing about this in the scientific literature today. Not because it's proven, it isn't, but because it's the first time anyone had proposed a mechanism that ties together two of the strangest, oldest mysteries about this planet, what those blobs at the base of the mantle actually are, and what really happened to the world that made the moon, into a single, coherent, testable idea. And I promised you a withheld thread earlier, so let me pull it tight now. The elevated iron signature in the moon's rocks. The elevated iron signature Yuan's team modeled for Theia's mantle. The measured density difference in the actual LLSVP, sitting at the core mantle boundary today. 3 separate lines of evidence from 3 completely different techniques: lunar geochemistry, computer modeling of an ancient collision, and seismic tomography of the modern Earth, all pointing tentatively toward the same iron-rich signature. That's not proof, but that's the thread the whole hypothesis hangs from, and it's a genuinely elegant one. Now, before you take this as settled fact, because I promised you honesty, and this is exactly where I have to deliver it, I need to walk you through the other side. Because a lot of serious scientists don't think Yuan is right, and their alternative explanation is in some ways just as strange. The rival explanation is older, more established, and honestly, it doesn't need another planet at all. It just needs this one, working the way we already know it works. Picture the surface of the Earth, not as it is now, but as a slow-motion conveyor belt running over hundreds of millions of years. Oceanic crust forms at mid-ocean ridges, spreads outward, cools, thickens, and eventually, at the edges of ocean basins, it dives back down into the mantle at subduction zones, one plate sliding beneath another, sinking into the depths. That's not speculation. That's measured, mapped, and about as settled as plate tectonics gets. Now, ask what happens to all of that sunken crust over deep time. It doesn't just vanish. Some of it, according to this model, sinks all the way down, through the entire thickness of the mantle, a journey that can take hundreds of millions of years on its own, and comes to rest at the very bottom, at that same core mantle boundary, where it slowly piles up. Scientists who favor this explanation call it, evocatively, a slab graveyard. Billions of years of dead ocean floor, dragged down plate by plate, accumulating into exactly the kind of large, chemically distinct structure that seismic tomography would pick up as a low shear velocity zone. And there's something almost eerie about how this model lines up geographically. Some researchers have tied the rough locations of these accumulated slabs to the breakup of an ancient supercontinent called Rodinia, something like 750 million years ago, long before Theia, long before the moon existed in anything like its current form, long, long before anything resembling a human eye existed to look up and see it. If the slab graveyard model is right, what Dziewonski heard in 1984 isn't the corpse of another planet. It's a compost heap, a billion years of tectonic recycling, quietly piling up in the one place on Earth nothing ever escapes from, the floor of the mantle itself. There's a third camp too, and I think it deserves its own breath because it's the strangest of the three in its own quiet way. Some scientists argue the material at the base of the mantle isn't foreign at all and isn't recycled crust either. It's primordial. Left over from the very first moments Earth differentiated into layers, when the planet was young enough that its interior hadn't yet fully separated into the neat onion shell structure we picture today. In this view, the anomalies aren't wreckage from a collision or debris from plate tectonics. They're leftovers from the planet's own birth, material that never finished sorting itself out, still sitting exactly where it settled before Earth had oceans, before it had a moon, before it had almost anything. 3 explanations: a dead world's mantle, a graveyard of sunken ocean floor, or the untouched afterbirth of the planet itself. And here's the part that I think matters more than picking a winner. Serious, credentialed research groups are actively working on all 3 of these, right now, in the same journals, arguing with each other in print. The slab graveyard idea has the deepest roots and the widest acceptance among specialists, simply because plate subduction is such a well-established process. The Theia impact idea is the newest and the most sensational, and it's the one that made the cover of Nature, in part because of how audacious the implication is. Nobody has definitively ruled out any of the 3. What almost all of them agree on is stranger than the disagreement itself. Whatever this material is, dead planet, dead ocean floor, or ancient placenta, it appears to be doing something to the rest of the planet. It isn't just sitting there, inert, at the bottom of everything. It seems to be leaking. Here's what I mean. If you take a global map of every major volcanic outpouring over the last 300 million years, the kind of eruption event geologists call a large igneous province, floods of lava so enormous they can reshape climate and trigger extinctions, and you plot those eruption sites on a map, then trace a line straight down, thousands of kilometers to the base of the mantle, something strange happens. Those lines don't land in the middle of the 2 LLSVPs, they land at the edges. Almost every one of them, clustering along the margins of these structures, like something is escaping specifically from the rim, not the body. It gets more immediate than ancient eruptions, too. There are roughly 24 active volcanic hotspots on Earth right now, the kind of persistent, long-lived volcanic activity that doesn't sit at a plate boundary, the kind that built Hawaii, for instance, one island at a time, as the Pacific plate crept slowly over something fixed and hot underneath it. Trace those hotspots down through the mantle to the core, and the same pattern holds. They line up with the margins of the 2 anomalous zones, not their centers. This correlation isn't controversial. It's about as well documented a spatial pattern as you'll find in deep Earth geophysics. 24 active columns of magma work their way up from the depths of this planet, and they consistently trace back to the rim of exactly the same structures that might or might not be the remains of another world. What's still genuinely argued over is the mechanism, what is actually rising, why it rises specifically at the edge and not the middle, and whether the material feeding those plumes carries any trace of whatever these anomalies are actually made of. Picture it like smoke rising from the rim of a smoldering pile, never from its center. That's the image seismologists reach for, because it's almost exactly what the data shows. Something at the edges of these 2 continent-sized structures is disturbed enough, hot enough, buoyant enough to break loose and rise nearly 3,000 kilometers through the entire thickness of the mantle, eventually breaking the surface as a volcano you could stand next to. Sit with that for a second. Some of the very ground that is erupted from underneath Hawaii, underneath Iceland, underneath places tourists visit to watch lava glow at night. Some of that material may have begun its journey at the ragged edge of a structure that could be the buried mantle of the world that made your moon. You have quite possibly stood on rock that started as a crack in a corpse 4.5 billion years old. And still, nobody has ever touched the thing itself. Nobody ever will, not with any technology we can currently imagine. I think it's worth knowing exactly how far out of reach it actually is, because the number is almost comic in how small it makes our best efforts look. In 1970, in the far north of what was then the Soviet Union, engineers began drilling straight down into the Kola Peninsula. Not for oil, not for minerals. Out of pure scientific curiosity about how deep a hole humans could actually put into solid continental crust and what they'd find on the way down. They kept at it for 19 years, bit by bit, meter by meter, through granite that fought back the entire way until 1989, when they reached their final depth, 12,262 meters, about 7.5 miles straight down. It remains, to this day, the deepest hole ever drilled into the earth by human beings, and it had to stop, not because they ran out of ambition, but because the rock itself refused to cooperate. At that depth, temperatures reached around 180 degrees Celsius, nearly double what the engineers had predicted before they started drilling. Rock that deep behaves less like solid stone and more like something plastic, something that flows and closes back in on itself under its own heat and pressure. The drill bits couldn't survive it. The borehole couldn't stay open. 19 years of continuous effort, the full might of a superpower's engineering program behind it, and the planet simply would not let them go any deeper. Now hold that number next to the one I gave you earlier. 7.5 miles. That's the absolute limit of what humanity has ever physically touched, going down. The two anomalies sitting at the base of the mantle are roughly 240 times deeper than that. I want you to actually feel the gap in that number, because it's easy to let a phrase like 240 times deeper wash over you as just another statistic. Picture the deepest hole ever drilled by human hands as a single splinter lodged just under the surface of your fingernail. Now picture the floor of the ocean, the actual seabed, miles beneath the waves, cold and lightless and utterly unreachable by a splinter that shallow. That's the scale difference between the deepest human reach and the depth where these anomalies sit. We are not close. We are not in the same order of magnitude of close. Every single thing anyone has ever claimed about what these structures are made of, how dense they are, how old they are, whether they're Theia or slab or primordial relic, every bit of it comes from inference. From listening to how the planet rings when it's struck, and from feeding that data into computer models built on our best understanding of physics and mineralogy. Nobody has held a piece of it. Nobody has looked at it under a microscope. Nobody, with current technology, ever will. There's something almost uncomfortable about that if you actually sit with it instead of skating past it. We know more, with more confidence, about the surface of Mars, a planet tens of millions of miles away, which we've landed rovers on, drilled into, photographed in obsessive detail. Then we know about a structure sitting 2,900 kilometers beneath the city you live in. We have driven wheeled robots across the red dust of another world. We have never so much as scratched the material sitting at the base of our own. That asymmetry is not an accident of funding or ambition, it's physics. Pressure at the core mantle boundary is measured in millions of atmospheres. Temperatures there rival the surface of the sun in some estimates. No metal, no ceramic, no material engineered by human hands could survive the trip down, let alone a return journey with a sample in hand. The deepest scar humanity has ever carved into this planet, the Kola borehole, didn't even make it 1/3 of the way there. If you scaled the whole depth of the Earth down to the height of an average adult, standing upright, the Kola borehole wouldn't even reach the ankle. The anomalies Yuan and Dziewonski and everyone in between have spent decades trying to characterize sit somewhere up around the ribs, maybe the collarbone, buried in tissue no human instrument has ever pierced, mapped only by the way a signal changes as it passes through, on its way somewhere else entirely. So on their way somewhere else entirely. And that phrase is worth pausing on because it turns out to be the key to something much bigger than just this one planet. Because the trick that let Dziewonski hear the shape of something he could never touch isn't unique to seismology. It's not even unique to Earth. It's one of the oldest tricks in the physical sciences, and once you notice it, you start seeing it everywhere. Think about the last time you or someone you know had an ultrasound. A technician runs a small device over skin, and sound waves, pitched far above what your ears can register, travel into the body, hit the boundary between different kinds of tissue, and bounce back at different speeds and intensities depending on what they hit. Muscle behaves differently than fluid. Bone behaves differently than either. The machine doesn't see any of this directly. It never can. It only measures how the signal changes on its way back out, and from that change alone, it builds a picture of an unborn child, or an organ, or a tumor nobody could otherwise find without cutting the body open. It is, mechanically, precisely the same idea as what happened at the base of the Earth's mantle. A signal enters something opaque. It changes speed, or bends or slows, depending on what it passes through. And from nothing but that change, a shape emerges that no eye has directly seen. Oil and mineral companies have been using a version of this for the better part of a century, sending controlled shock waves into the ground and reading the echoes to find pockets of oil, gas, and ore buried thousands of feet down long before anyone drills a single exploratory well. Engineers read the reflected signal, not the ground itself, and from that reading alone, they decide where tens of millions of dollars of drilling equipment should go. And the same exact principle, scaled up to a size that's almost impossible to hold in your head, is how we found out that black holes collide. In 2015, an instrument called LIGO detected something that had never been directly observed before, a ripple in the fabric of space and time itself, arriving at Earth after traveling for over 1 billion years, caused by two black holes spiraling into each other and merging somewhere far beyond anything a telescope could ever resolve. Nobody saw that collision. No camera, no telescope, nothing with a lens was pointed at the right spot at the right moment. What LIGO caught was a signal. An infinitesimally small stretching and squeezing of space, moving through the detector, changing its shape by an amount smaller than the width of a proton. And from that change alone, scientists reconstructed the mass, the distance, the violence, the entire shape of an event that happened in complete darkness, 1 billion light years from anyone who could ever have witnessed it directly. A doctor reading a sonogram, a geologist reading a seismic survey, a physicist reading a wobble in a laser beam sensitive enough to notice the universe flinch, and a seismologist in 1984 reading the timing of earthquakes to find 2 continent-sized shapes hidden inside his own planet. 4 completely different fields, 4 completely different instruments, 4 completely different scales, from the inside of a womb to the collision of black holes 1 billion light years away, and all 4 of them are doing the same fundamental thing. None of them are looking at the thing itself. All of them are listening to how something else changes on its way past it and trusting that the change carries the shape of what caused it. That is, without exaggeration, one of the more elegant ideas in the whole of science, that you do not need to touch a thing to know it's there. You do not need to see a thing to know its shape. You only need something to pass through it, or near it, or around it, carrying evidence of the encounter back out to wherever you happen to be standing, waiting to listen. And what makes the Earth's own version of this trick so strange to sit with is what it might be telling us it found. Not an oil deposit, not a tumor, not a distant, abstract cosmic event that happened somewhere else, to someone else, 1 billion years before anyone alive today existed. This time, the signal traveled through something that might be the actual physical surviving remains of another planet, one that no longer exists as a separate world because it died so that the moon, and the tides, and the tilted axis that makes a stable, livable Earth possible could exist in its place. Think for a second about what the moon actually does for you, personally, every single day of your life, whether you ever look up at it or not. It pulls at the oceans twice a day, dragging tides in and out along every coastline on Earth, tides that shaped where early life could cling to land instead of drifting forever in open water. It drags gently at the Earth's own rotation, slowing it, stretching the length of a day out over billions of years into something long enough for weather patterns and seasons and stable climates to exist at all. And most importantly, it locks the tilt of this planet's axis in place. Without a moon of roughly this size, sitting roughly this close, at roughly this angle, Computer models suggest Earth's tilt could wander chaotically over time, swinging wildly enough over millions of years to turn temperate zones into ice and ice into desert again and again, with no stability for anything complicated to evolve inside of. None of that happens without a body slamming into early Earth hard enough to blow a moon-sized chunk of material into orbit. The stability you take for granted every single day, every sunrise roughly 12 hours after every sunset, every season arriving on schedule, every tide you've ever stood in as a kid without knowing what held it in rhythm, all of it is the direct inheritance of a catastrophe. A planet had to die, essentially instantly, in a collision so violent it partially melted the Earth itself, so that the Earth you were born onto could hold still long enough for you to exist on it. You already knew that, on some level, in the abstract. Most people who've ever glanced up at a full moon have heard some version of the giant impact story. What almost nobody carries around in their head day to day is the other half of that story. The half Yuan's hypothesis is asking us to consider that the body of the thing that hit us didn't simply scatter into space and vanish, that most of Theia, if this idea holds up, never left at all. It went down, not out. Iron-rich, too dense to stay mixed into the churning young mantle above it, sinking slowly over unimaginable stretches of time until it settled at the one place in this entire planet nothing else can reach, the boundary between rock and molten metal, 2,900 kilometers beneath wherever you happen to be sitting right now. Which means, if Yuan is right, you have never, for one single day of your life, stood on a planet that was entirely, purely, only Earth. You have spent your whole life on top of two graves. One is empty, the visible one hanging in the night sky, made of debris that escaped the collision and cooled into the moon. You've watched your entire life without ever once suspecting it was a monument. The other grave is full, and it is the one nobody can see, because it never left the crime scene. It has been sitting exactly where it landed since before there was an atmosphere to breathe, before there was liquid water, before there was a single living cell anywhere on this world, quietly holding its shape at the bottom of everything, while continents assembled and broke apart above it, while oceans filled and emptied, while every single living thing that has ever existed on this planet, every animal, every plant, every one of your ancestors going back past the first spark of anything recognizable as life, lived and died directly on top of it without knowing. And here's the part that I think is genuinely hard to hold on to for more than a few seconds at a time, because it slips away the moment you stop concentrating on it. The only reason you can stand up, breathe air that stays where it's supposed to, live through seasons that arrive on a schedule stable enough for agriculture, for civilization, for you, is that a planet died catastrophically enough to leave a piece of itself in the sky every night, and, very possibly, the rest of itself directly beneath your feet right now, unmelted, unmixed, waiting there in the dark for a species that wouldn't exist for another 4.5 billion years to learn how to listen for it. We found it not by seeing it, not by touching it. We found it because something we could never reach still managed to leave a signature in the way the whole planet rings when it's struck. The same way you learn the shape of a bruise you can't see, from nothing but how the skin sounds under your own hand. Let me walk you through what sinking actually means physically, because the word makes it sound faster and more dramatic than what's actually happening down there, and the reality is stranger than the word suggests. The mantle is solid rock. It is not molten, not liquid, not anything you'd recognize as fluid if you dropped a piece of it in front of you at room temperature. And yet, under the pressure and heat found deep inside this planet, over spans of time too long for a human mind to really hold on to, that solid rock flows. Not like water, not even like honey, more like something closer to glass or asphalt on a hot day, so thick and so slow that a chunk of it might move only a few centimeters in an entire year, roughly the speed your fingernails grow. That is the pace at which the entire mantle convects, endlessly, churning heat up from the core toward the surface, dragging cooler material back down to replace it in a cycle that has been running since this planet was young. So when Yuan's modeling describes chunks of Theia's mantle, tens of kilometers across, sinking through Earth's mantle after the impact, That sinking isn't a plunge. It isn't gravity yanking a stone to the bottom of a pond in a few seconds. It's a journey measured across what could be hundreds of millions of years, chunk by chunk, fraction of an inch by fraction of an inch, through rock that is technically solid the entire time. And once that material finally reaches the core mantle boundary, once it settles into place atop the core, the same slow convection that carried it down there keeps moving everywhere around it, without ever managing to drag the material itself back up and mix it in. Picture two boulders sitting in the bed of a river. The water never stops moving. It rushes over the boulders around them, forming eddies and currents on every side, endlessly circulating. But the boulders themselves stay exactly where they are, too large and too dense for the current to carry off. That's a reasonable way to picture what mantle convection is doing to these two anomalies right now, at this very moment, while you're listening to this. The rest of the mantle keeps circulating, keeps carrying heat upward, keeps completing its slow multi-hundred-million-year loops, and the two structures at the bottom simply don't participate. They sit there, stable, while everything else moves around them, the way it may have been doing since not long after the moon-forming impact itself. This is also, if you think about it for a moment, the reason these structures could have survived at all. A blob of unusual material dropped into a vigorously churning mantle would ordinarily be expected to stretch, thin out, and eventually mix into the background rock, the way a drop of ink stretches into thin filaments in a stirred glass of water and eventually disappears. That doesn't seem to be what happened here. And the working explanation is exactly the density difference we talked about earlier. That 2 to 3.5% figure from UN's modeling isn't just a curiosity. It's the reason the material never got shredded into the rest of the mantle in the first place. It was too heavy to be pulled along by the same currents, dragging everything else through its slow circulation. It dropped out of the current entirely, the way a heavy stone dropped into a swirling stream will find the bottom and stay there, indifferent to the water still rushing past it. Mineral physicists have taken this question into the laboratory, in a much more literal sense than you might expect. Researchers have built devices capable of squeezing tiny samples of rock and mineral between the tips of diamonds, generating pressures that begin to approach what exists at the base of the mantle, while simultaneously blasting them with lasers to reach comparable temperatures. A brutal, miniature reenactment of the conditions 2,900 kilometers down, run on a sample smaller than a grain of rice. From experiments like this, combined with the seismic data, scientists have built increasingly confident models of how dense, how stable, and how chemically distinct this material would need to be to explain what Dziewonski first heard in 1984. And it's from that overlap, seismic timing data on one side, laboratory mineral physics on the other, that the chemically distinct, not just hot conclusion actually comes from. Two completely independent methods, one listening to earthquakes, one crushing rock between diamonds, converging on the same answer. I keep circling back to how strange the timescale is here, because I don't think it's possible to overstate it, and it's easy to let a phrase like billions of years become just a sound rather than a magnitude you actually feel. Since the moon-forming impact, continents have assembled into supercontinents and broken apart again, not once, but repeatedly. Rodinia, the one we mentioned earlier, tied to the slab graveyard hypothesis, was only one chapter in that story, and it broke apart something like 750 million years ago, meaning it formed, existed, and dissolved entirely within a single one of the many supercontinent cycles this planet has cycled through since Theia struck. Entire oceans have opened and closed, the very first single-celled life appeared, and then, after a span of time so long it makes the age of the dinosaurs look recent, multicellular life followed. Every mass extinction this planet has ever suffered, and there have been several, each one wiping out the overwhelming majority of species alive at the time, happened while whatever is sitting at the base of the mantle stayed exactly where it was, undisturbed by any of it. Nothing that has ever lived, moved, evolved, or gone extinct on the surface of this world has so much as nudged the structure sitting at its core. There's a particular way scientists sometimes describe two very different materials that look alike on the surface but respond differently under stress. They say the materials ring differently when struck. The way two bells cast from different metals will each produce a distinct tone, even if they're the same size and shape. That's a fair way to think about what Dziewonski's instruments actually detected, decades before anyone proposed Theia as an explanation. Two regions of the deep earth that, if you could somehow reach in and strike them, would ring at a different pitch than the rock around them. Not because they're shaped differently, not because they're positioned strangely, but because whatever they are made of is not the same substance as the rest of the planet. A bell within a bell, tuned to a different note, and nobody on the outside able to hear the difference except by tapping the whole planet and comparing echoes across a global network of instruments, patiently, for years, the way Dziewonski did. There's one more honest complication I need to give you, because leaving it out would make this sound more settled than it actually is, and settled is not the same as true. Everything I've told you about Theia rests on one foundational assumption, that the giant impact hypothesis itself, the idea that a Mars-sized object struck early Earth and formed the Moon, is correct. And I want to be straight with you. It is the leading model. It's the model most planetary scientists work from, the one that best explains the Moon's overall composition, its orbit, its size relative to Earth. But leading is not the same as unanimous, and there are other ideas still alive in the field. Some researchers have proposed that instead of one single decisive collision, the Moon might have formed from a series of smaller impacts over time, each one flinging a bit more debris into orbit, gradually building up the body we see today, rather than assembling it in one catastrophic afternoon. Others have proposed something stranger still, a scenario researchers call a synestia, a temporary donut-shaped cloud of vaporized rock and metal, spun up so hot and so fast by an impact that it doesn't behave like a solid planet and a solid impactor colliding at all, but more like two clouds of superheated gas merging into one swirling structure, out of which the Earth and Moon both eventually condensed and cooled as separate bodies. It's a genuinely strange picture, closer to something you'd imagine happening inside a star than what most people picture when they hear two planets collided. I raise this not to undercut the story, but because it matters for how much weight the Theia blob hypothesis can actually carry. If the Moon didn't form from one clean, singular impact, if the truth is closer to multiple smaller strikes or a swirling synestia that Earth and Moon both crystallized out of together, then the entire premise of a single displaced planet's mantle sinking to the core in one coherent mass gets murkier. UN's hypothesis is built specifically on the classic single giant impact picture. It's the version most consistent with the current evidence and the version most planetary scientists still favor. But it isn't the only version on the table, and an honest telling of this story has to say so. There's a second honest complication, sitting closer to home, back at the two anomalies themselves. I told you their boundaries have been mapped, their rough size estimated, their depth pinned down to the base of the mantle. What I haven't told you is that even those basic properties are still argued over among the people who study them most closely. Exactly how sharp the edges of these structures are, whether they end abruptly like a cliff face or fade gradually into the surrounding mantle over some transition zone, is a live question, and different studies using different seismic techniques get different answers. Whether the structures are genuinely static, locked in place and essentially unchanged since not long after they formed, or whether they're slowly evolving, shifting shape over tens or hundreds of millions of years as convection nudges at their margins, is likewise unresolved. Even the overall volume estimate, that 6 to 9% of the mantle figure, isn't one clean number agreed upon by everyone. It's a range, because different tomographic models draw the boundary of anomalous material slightly differently, and reasonable scientists working from the same underlying data can arrive at meaningfully different totals. None of this uncertainty erases what Dziewonski found in 1984. The anomalies are real. Every serious researcher in this field agrees they exist, agrees roughly where they are, agrees roughly how large they are. What's contested sits one layer deeper, not whether there's something down there, but what precisely that something is, how sharply it's bounded, and whether it has held its shape since the earliest days of this planet, or is still, this very moment, quietly changing. For decades before Yuan ever connected any of this to the base of the mantle, planetary geochemists had already been quietly wrestling with a puzzle sitting in trays of lunar rock, brought back by astronauts and stored in secure facilities, studied over and over by generation after generation of scientists. Those samples let researchers measure, precisely, the ratios of different elements locked inside lunar rock, and one of those ratios never quite added up the way the simplest version of the giant impact story predicted. If the moon really did form mostly from debris flung off of early Earth, you'd expect its overall chemistry to closely mirror Earth's own mantle, like a child bearing an obvious resemblance to a parent. And in many respects, it does. That resemblance is one of the strongest pieces of evidence for the giant impact story in the first place. But that elevated iron oxide content kept showing up stubbornly across sample after sample, a chemical trait that fit less comfortably into the mostly Earth material picture. For years, this was treated as a loose thread in an otherwise well-supported story. Not a crisis for the giant impact hypothesis, but a detail nobody had fully explained. A quiet asterisk sitting in the geochemistry literature, waiting for someone to notice it might connect to something else entirely. What Yuan's team effectively did was reach across two different scientific literatures that had been sitting side by side for years without touching. The geochemists puzzling over lunar iron content on one side, and the seismologists mapping strange, dense structures at the base of the mantle on the other, and ask whether the same iron-rich source material could explain both anomalies at once. Not two separate unsolved puzzles, possibly one. That's the move that turned a decades-old asterisk in lunar geochemistry into a testable headline-making hypothesis about the deep structure of the entire planet. And it's worth sitting with how long that asterisk sat there, waiting. The Apollo samples had been back on Earth, studied, cataloged, and reanalyzed with steadily improving instruments for the better part of half a century, before anyone thought to connect their chemistry to a pair of seismic shadows discovered independently by a completely different kind of scientist, using a completely different kind of instrument on the opposite side of the world from where any of those rocks were sitting in storage. Take a breath, right now, and feel your chest rise. That air moving in and out of you exists in its rhythm, on a planet spinning at a tilt that hasn't wandered off into chaos, orbited by a moon that is hung in the same sky for every sunrise anyone has ever watched. None of that was guaranteed. All of it was bought by a catastrophe old enough to make every human story that has ever been told look like it happened seconds ago. Somewhere below you, right now, two shapes the size of continents are sitting exactly where they've sat since before there was air to breathe at all. Patient, silent, ringing a different note than the rock around them, waiting for nothing, because they don't need anything from us. We are the ones who needed to find them. We built instruments sensitive enough to hear a shadow we will never see, and traced it back to the possibility that a piece of another world has been lying beneath our feet since before feet existed to stand on it. We don't know, not for certain, whether what's down there is Theia, or a graveyard of ancient ocean floor, or something older than either, left over from the planet's own birth. Maybe we never will know for certain. But the not knowing is its own kind of wonder, proof that there is still a version of down there as unmapped and as strange as anything out there has ever been. So the next time you look up at a full moon, let yourself picture the other half of that story. Not hanging in the sky, held in the dark, at the bottom of everything, still keeping its shape. Breathe again. You are standing on top of a grave that made your life possible.